What if everything you see, the galaxies, matter, even time, arose from a simple fluctuation in the vacuum? This audiobook explores one of the boldest ideas in modern cosmology, that the universe may have been born from nothing, driven by a spontaneous quantum variation. Through the latest science, we will discover how the microscopic chaos of the vacuum could hide the origin of everything we know. The quantum fluctuation can be compared to the gentle movement of waves on a lake. Although the water appears calm on the surface, there are constant changes and small disturbances beneath. Similarly, in the vast vacuum of the universe, where it seems there is nothing, small bubbles of energy arise that can give rise to particles. This happens so quickly and fleetingly that in an instant they can appear and disappear like sparks from a fire flickering in the dark. Now, one must ask, how can these small fluctuations influence something as colossal as the universe? The answer lies in the fact that in the first fractions of a second after the Big Bang, our universe was in an extremely hot and dense state. In that primordial moment, quantum fluctuations played a fundamental role, sowing the seeds of matter and energy that would eventually transform into galaxies, stars, and planets. To illustrate this phenomenon, imagine a field full of flowers. Each flower represents a point in the universe. Quantum fluctuations are like the wind that stirs the flowers, causing some to grow more than others. This difference in growth can lead to the formation of structures in the cosmos, from the smallest to the largest. Without those small variations, the universe as we know it would not exist. The importance of quantum fluctuation is not limited solely to the creation of matter. This concept is also intertwined with the very nature of the vacuum. In quantum mechanics, the vacuum is not simply an empty space, it is full of potential. It is a place where particles can arise from nothing, challenging our classical understanding of reality. This revolutionary view forces us to rethink what we understand by nothing. In our quest to understand the origin of the universe, quantum fluctuation offers us a unique perspective. It leads us to explore beyond the visible, delving into the world of the subatomic. Here, the rules that seem to govern our day-to-day lives become blurry and fascinating. It is a reminder that reality is much more complex and astonishing than our senses can grasp. An intriguing question arises. Is it possible that the entire universe is the result of a simple quantum fluctuation? This idea may seem far-fetched, but many physicists and cosmologists consider it a possibility. If the universe began as a small fluctuation in the quantum vacuum, then the very essence of our existence could be linked to these random and fleeting events. The evolution of these ideas has led scientists to consider increasingly complex and fascinating models of the creation of the cosmos. For example, the Big Bang theory, which proposes that the universe began as an infinitely small and hot point, merges with quantum mechanics to offer a coherent view of our origin. But how far can we go in trying to understand the beginning of everything? As we delve into this field, we encounter a labyrinth of theories and concepts that challenge our intuition. The relationship between quantum fluctuation and the expansion of the universe leads us to think about how what we see and know today was once an energetic chaos where the improbable became possible. This journey invites us to question not only the nature of the universe but also our own existence. The study of quantum fluctuation thus becomes a crucial tool for unraveling the mysteries of the cosmos. It pushes us to look beyond what is evident, to accept that reality can be as strange as it is wonderful. Each discovery in this realm brings us one step closer to understanding the fabric that connects everything that exists, from the tiniest particles to the most distant galaxies. In this context, it is vital to recognize that we are just beginning to scratch the surface of knowledge in cosmology. As we advance in our exploration, each answer we find only generates more questions, keeping the spark of human curiosity alive. What other surprises does the universe hold for us? What secrets remain hidden in the depths of the quantum vacuum? With each new theory and experiment, the field of cosmology expands, challenging our perceptions and broadening our understanding. And so, as we contemplate the vastness of the cosmos, we must remember that, in the end, everything may have begun with a simple fluctuation, a spark in the immensity of the vacuum. These are the questions that drive us to keep investigating and to continue dreaming big, for the universe, with all its mysteries, invites us to keep exploring the unknown. Quantum fluctuations are an intriguing phenomenon that may seem like they are straight out of a science fiction novel, but in reality, they are part of the very fabric of our universe. What exactly are they, and why are they so important? To understand this, we first need to delve into the fascinating world of quantum mechanics, where the rules are very different from those we are accustomed to in our daily lives. Imagine for a moment that the vacuum is not simply the absence of something, but a place filled with activity. In the quantum world, even the vacuum is brimming with energy and potential. This quantum vacuum is like a pressure cooker, although it appears inert at first glance. Inside it, there is a constant dance of particles that appear and disappear in the blink of an eye. This phenomenon is known as quantum fluctuation. But how can something arise from nothing? Quantum fluctuations are like bubbles that emerge and burst in a sea of energy. In this context, subatomic particles can appear and disappear almost instantaneously. Sometimes these bubbles grow large enough to be detected. Thus, the vacuum becomes a vibrant place where the creation and destruction of particles is a continuous process fundamental to everything we know. Now, if the vacuum is so full of activity, how do we know these fluctuations exist? Throughout the history of physics, scientists have formulated theories and conducted experiments that support the existence of this phenomenon. For example, the energy of the vacuum has been indirectly measured through effects like the Casimir effect, where two plates that are very close to each other experience an attractive force due to the quantum fluctuations of the vacuum between them. This experiment is a window into an invisible world that surrounds us. Quantum fluctuations are not just a whim of theoretical physics, they have very real implications. They are thought to have played a crucial role in the birth of the universe itself. When the universe was forming, these fluctuations may have given rise to the seeds of matter that would eventually clump together to form galaxies, stars, and planets. So, in a sense, every star we see in the sky may have begun as a small bubble of energy in a quantum vacuum. But why is quantum fluctuation so relevant in our quest to understand the cosmos? The answer lies in its ability to challenge our most fundamental notions of reality. It forces us to question what we consider empty and nothing. Quantum mechanics teaches us that the universe is much stranger than we can imagine, where the rules of logic seem not to apply in the same way. Moreover, quantum fluctuations may be the key to understanding phenomena such as dark matter and dark energy. These are entities that, although we cannot see directly, seem to play a fundamental role in the structure and expansion of the universe. By understanding how quantum fluctuations can influence them, we could clear up some of the biggest mysteries of contemporary cosmology. The idea that the universe may have arisen from a simple quantum fluctuation is undoubtedly fascinating, but it also raises profound questions. If everything we know began from a small variation in the vacuum, what does that mean for our perception of reality? Are we in some way connected to that quantum vacuum that gave rise to everything? As research progresses, quantum physics challenges our intuitions and invites us to explore beyond the limits of our understanding. Quantum fluctuations teach us that reality is more complex and rich than we can see at first glance. This phenomenon pushes us to think of a universe in which everything is interconnected, where the vacuum is not a place of absence, but a space of infinite possibility. The implications of quantum fluctuations are not limited to the realm of physics. Philosophically, this concept invites us to reflect on the nature of our existence. If the universe can arise from nothing, what does that mean for our own lives and our place in the cosmos? Could our own existence be the result of a quantum event? Throughout history, humanity has sought answers to questions about its origin. Quantum fluctuations offer us a new perspective, illuminating a path toward understanding how the universe was formed. Although there is still much to discover, the study of this phenomenon provides us with a window into a hidden world full of surprises and mysteries that we are still trying to unravel. Ultimately, quantum fluctuations are not just a fascinating topic in modern physics. They are also an invitation to continue exploring and questioning. Each discovery in this field brings us one step closer to unraveling the secrets of the universe and our own existence. In this journey, we find ourselves not only as observers but as active participants in the cosmic story unfolding around us. Have you ever stopped to think about how it all began? The idea that the universe had a beginning is fascinating and, at the same time, complex. The Big Bang Theory offers us a captivating narrative about the origin of the cosmos. But what does the term Big Bang really mean? Essentially, it refers to the event that gave birth to the universe as we know it, a monumental explosion that occurred approximately 13,800,000,000 years ago. However, this is not just a story of explosions and chaos. It is the tale of how everything that exists today began from an infinitesimal point. When thinking about the Big Bang, it is helpful to imagine it as a balloon. When we inflate a balloon, we start with a small point of air, and as we fill it, it expands and comes to life. Similarly, the universe began as an extremely hot and dense point that in an instant started to expand, giving rise to all the matter and energy we know. This process was not simple. It was an event that marked the beginning of time and space, transforming nothing into something. Now, what happened in those first moments after the Big Bang? In the blink of an eye, the universe expanded and cooled, allowing subatomic particles to begin to form. But why is it crucial to understand this? Because these first particles laid the groundwork for everything that exists. Stars, planets, and even ourselves. Without that initial burst of energy, the cosmos we inhabit today would not exist. It is interesting to think that although the Big Bang is the beginning of our cosmic story, it was not an isolated event. The theory suggests that during the early moments, the universe experienced what we call cosmic inflation, a period of extremely rapid expansion that helped shape the structure of the universe. But what exactly is cosmic inflation? Imagine that the universe, in its early moments, was stretching like a balloon that is rapidly inflating, growing exponentially in a fraction of a second. This initial expansion was key to ensuring that matter was distributed evenly, preventing the universe from collapsing in on itself. It is astonishing to realize that although today the universe seems vast and infinite, in its early moments it was a very different place during that era of formation. The universe was a soup of particles and energy where gravity and other fundamental forces were beginning to take shape. But how do we know this is true? In science, evidence is fundamental. Astronomers and physicists have collected data through observations of galaxies, cosmic microwave background radiation, and other phenomena that support this theory, revealing a universe in constant evolution. One of the most intriguing pieces of the puzzle is the cosmic microwave background radiation. This is like the echo of the Big Bang, a signal that reaches us from the farthest corners of the universe. Imagine a campfire that has left ashes. Those ashes are what remains of a once great flame. The background radiation is the trace of that great explosion, a footprint that tells us what the universe was like when it was just a few 100,000 years old. That information is invaluable to scientists who can reconstruct the history of the cosmos from it. As the universe continued to expand and cool, the first atoms of hydrogen and helium began to form. This was a crucial step, as these elements are the building blocks of stars. Without hydrogen, there would be no stars or galaxies. But how did those first stars form? Over time, clouds of gas collapsed under the influence of gravity, igniting the first nuclear fusions and creating the light that would illuminate the universe. It is fascinating to consider that every star we see in the sky, every galaxy we can observe, has its origin in that colossal event billions of years ago. However, as the universe expanded, it also cooled, allowing for the formation of more complex structures, but it was not all a straight path. The history of the universe is full of unexpected twists, such as the emergence of dark matter and dark energy, mysterious forces that seem to dominate the cosmos. Dark matter is a fundamental component that we cannot see, but we know it is there due to its gravitational influence. On the other hand, dark energy is even more perplexing, acting as a force that accelerates the expansion of the universe. These two entities are like invisible actors in a cosmic play, guiding the fate of the universe from the shadows. General relativity, formulated by Albert Einstein, provides us with a framework for understanding how gravity interacts with matter and energy in the universe. Through this theory, we can visualize how cosmic structures form and evolve over time. It is a reminder that the universe is a dynamic place, where every action has its reaction, and every star, every galaxy, has its story. As we explore these ideas, it is essential to remember that the Big Bang is not just a theory, it is a testament to our curiosity and desire to understand the cosmos. Questions about our origin are profound and relevant, and every answer we find leads us to new questions. What lies beyond the Big Bang? Is it possible that other universes exist? These questions invite us to continue exploring and learning, to keep searching in the vast ocean of knowledge. The story of the Big Bang is just the beginning of a much broader narrative. As we delve into the mysteries of cosmology, each discovery opens new doors to understanding. The universe is full of surprises and wonders, and each step we take toward its understanding brings us a little closer to the truth of our place in the cosmos. If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey. Cosmic inflation is such a fascinating concept that it may seem almost magical. How is it possible that the universe, which today appears so vast and expanding, began in such a small and compact form? The idea that in an incredibly brief moment the universe expanded at an unimaginable speed is truly astonishing. But what does this cosmic inflation really mean? To understand it, it is helpful to imagine a balloon. When we inflate a balloon, it starts off very small, but as we blow air into it, it expands rapidly. Something similar happened in the early universe. In the first moments after the Big Bang, it is believed that the universe experienced exponential expansion, growing from the size of a subatomic particle to a size that encompassed everything we know in the blink of an eye. This phenomenon not only explains why the universe looks the way it does today, but also addresses several mysteries that have intrigued us for decades. One of those mysteries is the uniformity of the universe. If we look up at the sky, we find extremely distant regions that, despite being separated by vast distances, seem to have the same temperature and density. How is that possible? Cosmic inflation suggests that before this explosion of expansion, those regions were in contact and could balance their energy and temperature. Essentially, all those parts of the universe started from the same point and then quickly separated. But what caused this sudden expansion? Scientists have proposed that a form of energy called vacuum energy, or inflaton field, may have been present in the early universe. This energy would have had the ability to push space outward, causing the universe to inflate like a balloon. However, over time this energy dissipated, allowing the universe to continue expanding, but at a much slower rate. This leads us to the next intriguing question. How does this inflation affect the structure of the universe we observe today? The answer is related to the small fluctuations that occurred during that inflationary period. Imagine you are looking at a calm surface of water. If you throw a stone, you will create ripples that propagate. Similarly, during inflation, small irregularities were amplified, creating variations in the density of the universe. These fluctuations are the seeds of the galaxies and structures we see today. As the universe continued to expand, these fluctuations became areas where matter accumulated, forming stars and galaxies. Without inflation, we might never have seen the universe filled with the bright galaxies we know. This process helps us understand how matter and energy are distributed in the cosmos. But what about time? Cosmic inflation also offers us a new perspective on time itself. In the early moments of the universe, time as we know it may have been very different. With rapid expansion, time and space intertwined in ways we are still trying to comprehend. This raises philosophical questions about the nature of time. Is it a universal constant, or does it depend on the state of the universe? One of the most surprising implications of cosmic inflation is its relation to the multiverse theory. If the universe can experience this rapid inflation, could other universes exist, each with its own physical laws and characteristics? This idea may seem like science fiction, but some physicists consider it a real possibility, opening up a range of questions about our existence and the place we occupy in the vast cosmos. Cosmic inflation not only helps us understand the past of the universe, but also provides us with tools to look toward the future. By studying the small variations left by inflation, we can make predictions about the future evolution of the universe. Will it continue to expand forever, or will there come a time when this expansion slows down and the universe begins to contract? These are questions that scientists are eager to answer. Despite its complexity, cosmic inflation brings us one step closer to unraveling the mysteries of the universe. It leads us to reflect on the origin of everything we know and invites us to keep seeking answers. Could we be on the verge of a new discovery that changes our understanding of the cosmos? In summary, cosmic inflation is an astonishing phenomenon that transformed a tiny universe into the vast cosmos we inhabit today. Through it, we have found answers to many of our deepest questions while simultaneously raising new inquiries. The quest for knowledge never ends, and each answer generates more questions that push us to explore the unknown. The connection between quantum mechanics and cosmology is like an invisible thread that ties the small particles that make up matter to the vast universe that surrounds us. In this fascinating crossroads, the laws governing the subatomic world provide us with clues about the mysteries of the cosmos. But how can the principles of quantum mechanics influence the way we understand the universe? To begin with, let's think of quantum mechanics as a set of rules that describe a scenario in which particles do not behave like solid and predictable objects, but rather like actors in a theater where anything can happen. In this scenario, particles can appear and disappear, and their positions and velocities are, in a sense, a game of probabilities. Can you imagine a coin that, instead of landing on heads or tails, remains in a state of uncertainty, as if it were spinning forever? That is the essence of quantum mechanics. Now, what role does this play in cosmology? If we consider that the universe began to exist from a singularity, a point of infinite density, quantum mechanics suggests that chaos and uncertainty were present even in the earliest moments of creation. At that primitive moment, quantum fluctuations acted like sparks in a fireworks workshop, generating small variations that would eventually shape the grand structures of the universe we know today. Quantum fluctuations are like bubbles in a sea of possibilities, emerging and disappearing in an instant. These bubbles, although ephemeral, have the potential to leave a mark on the fabric of space-time. But how do these small bubbles translate into something as monumental as galaxies? The answer lies in the interaction of these fluctuations with dark energy and gravity, forces that shape the expansion of the universe. Imagine that each quantum fluctuation is like a small stone thrown into a pond. The waves that propagate from that stone can create patterns on the surface of the water, and similarly, quantum fluctuations can generate variations in the density of the universe. These variations are crucial as they act as seeds that, when influenced by gravity, can grow and become the galaxies and clusters of galaxies that we observe in the cosmos. An intriguing aspect of this relationship is the idea that quantum mechanics not only influences the universe on a large scale, but also provides us with a framework to understand its evolution over time. The laws of quantum mechanics are fundamental to the creation of the particles that constitute matter, and these particles in turn interact in ways that shape the history of the universe. Isn't it amazing to think that in the earliest moments, the laws of physics governing the smallest aspects of our existence were also responsible for the creation of the largest? The connection between quantum mechanics and cosmology leads us to reflect on the nature of time and space. If the universe began with an explosion of energy and particles, what is the nature of that first moment? Some scientists suggest that time, as we know it, may have begun at that moment of creation. In this sense, quantum mechanics not only provides answers about how, but also about why we exist. As we advance in our understanding of the cosmos, it is essential to remember that quantum mechanics and cosmology are two sides of the same coin. While quantum mechanics focuses on the world of the infinitely small, cosmology invites us to appreciate the vastness of the universe. Together, these disciplines allow us to explore fundamental questions about our place in the cosmos and the nature of reality itself. The relationship between these two areas also challenges our intuitions about the world. The idea that the universe may be the result of random events at the quantum level can be disconcerting. However, this randomness does not imply complete chaos. Rather, it suggests that there is an underlying order that, although not always evident, guides the evolution of the cosmos. In this context, it is exciting to think about the possibilities that open up before us. Quantum mechanics invites us to consider the existence of alternative realities and multiple universes, where each decision and each event can lead to different outcomes. The idea of a multiverse, where each quantum fluctuation gives rise to a distinct universe, leads us to question our understanding of reality and of ourselves. So, as we look up at the starry sky, let us remember that each star, each galaxy, is the result of an intricate dance between the quantum and the cosmic. Quantum mechanics is not just an isolated field of study, but a window into the deepest mysteries of the universe. By understanding how these small fluctuations have influenced the vast expanse of the cosmos, we come a little closer to answering the fundamental question of why we are here and how we came to be part of this amazing universe. Have you ever wondered what lies in the vacuum of space? You might think of the vacuum as simply that, an emptiness with nothing, but in quantum mechanics things look very different. In this fascinating world, the vacuum is not an empty place, but a bubbling sea of activity. This is where the concept of quantum vacuum comes in, an idea that may seem strange but has profound implications for our understanding of the universe. Imagine a calm lake. On its surface, everything appears tranquil and serene, but beneath the water there are currents and bubbles forming and disappearing. Similarly, the quantum vacuum is filled with fluctuations that we cannot see, but that are constantly occurring. These fluctuations are brief, almost imperceptible, but they can have a huge impact on the fabric of the universe. But what exactly are these quantum fluctuations? Essentially, they are temporary variations in the energy of the vacuum. According to quantum theory, the vacuum is not a state of zero energy. In reality, it is filled with virtual particles that appear and disappear in the blink of an eye. These particles are not like the ones we are used to thinking about, as they cannot be measured in the same way. However, their existence is fundamental to understanding how the universe works at its most basic level. An intriguing question arises from this. If the vacuum is so full of activity, can this activity give rise to something more? Surprisingly, the answer is yes. These fluctuations can generate real particles under certain conditions. In the early universe, just after the Big Bang, these quantum fluctuations may have been responsible for the creation of the matter that makes up everything we know today. It's as if the vacuum has a hidden potential, waiting for the right moment to manifest. The idea that the quantum vacuum can be so dynamic leads us to reflect on the nature of reality itself. If the vacuum is a place of continuous creation and destruction, does this mean that everything we see around us is the result of these little bubbles of energy appearing and disappearing? It's a fascinating thought that challenges our traditional understanding of what matter is. Often we think of the vacuum as something that opposes existence, but in quantum mechanics it is quite the opposite. The vacuum is a fertile field of possibilities. This raises another question: what else could arise from this vacuum? Some scientists suggest that there could be multiple universes, each emerging from different quantum fluctuations in the vacuum. Thus, the vacuum could be a kind of cosmic cradle where new universes are born. The relationship between the quantum vacuum and the creation of particles also has implications for the nature of energy. In this context, energy is not a fixed entity, but something that can arise from nothing. This challenges our perception of energy conservation, leading us to question whether the universe could have emerged from an initial quantum fluctuation. Moreover, the quantum vacuum not only generates particles, it also plays a crucial role in how they interact. These virtual particles can influence the fundamental forces that govern the universe. Therefore, the vacuum is not just a passive backdrop, but an active player in the fabric of the cosmos. Another fascinating aspect is how the quantum vacuum relates to gravity. Although gravity is a force that affects massive objects, its interaction with the quantum vacuum could reveal hidden secrets about the nature of space and time. This leads us to wonder, could the vacuum be the key to unifying quantum mechanics and general relativity? As we delve deeper into the quantum vacuum, we also encounter philosophical questions. If the universe can arise from nothing, what does this mean for our beliefs about creation and origin? Could it be that the essence of the cosmos is intrinsically linked to the idea that nothing is truly empty? The exploration of the quantum vacuum and its fluctuations takes us on a fascinating journey, where each answer generates new questions. As science advances, we are getting closer to unveiling the mysteries of this vacuum in which we live. And although the concept may seem complex, its essence is simple. The vacuum is an inexhaustible source of potential. So the next time you look up at the starry sky, remember that there is much more than meets the eye. The quantum vacuum is working behind the scenes, giving us clues about the origin of the universe and the very nature of reality. In this vast ocean of possibilities, quantum fluctuations are the whisper of creation, reminding us that even in the absence of matter, life and the cosmos are full of surprises. When we look at the starry sky, what makes us wonder how stars and planets formed? The answer to this question leads us to a fascinating concept: quantum fluctuations. But how can these small variations in the vacuum give rise to something as monumental as the particles that make up our universe? Quantum fluctuations are like ephemeral bubbles that appear and disappear from nothingness. Imagine a calm sea. Suddenly, a small wave rises from nowhere, only to fade away in an instant. This phenomenon occurs at the smallest level of reality, where the laws of quantum mechanics govern the behavior of particles. But what does this mean in terms of particle creation in the primordial universe? At the moment the universe began its journey, it was full of energy and potential. Quantum fluctuations acted like sparks in an extremely dense and hot environment. Think of a pot of boiling water. The bubbles that rise to the surface are like these fluctuations, which in the cosmic context can lead to the formation of particles. Each bubble that appears represents a possible particle that could exist. Now, how do these quantum bubbles become something tangible when the universe rapidly expanded in what we know as cosmic inflation? That energy and those fluctuations began to freeze into a more stable form, giving rise to the particles that make up matter. This process is similar to how water vapor turns into raindrops when cooled. The quantum fluctuations became the matter we see today. In the primordial universe, chaos and energy were the norm. Quantum fluctuations not only created particles but also helped establish the balance that allowed matter to organize into more complex structures. But what about the forces that hold these particles together? This is where symmetry and its breaking play a crucial role. Symmetry in physics is like a beautiful design on paper. Everything seems to be in balance and harmony. However, when this symmetry is broken, forces are generated that shape the universe. In the case of quantum fluctuations, the breaking of symmetry allowed some particles to acquire mass while others remained light. This process is fundamental to understanding how galaxies and stars formed from a primordial state of chaos. Some theories, such as string theory, suggest that we might even live in a multiverse where each quantum fluctuation could give rise to a distinct universe. It's as if each bubble that appears in our quantum sea could be a window to a different universe. Can you imagine all those possible realities, each with its own characteristics and physical laws? It's a concept that makes us reflect on the nature of our own universe. Quantum fluctuations are not only responsible for the creation of particles, they also teach us about the very nature of the vacuum. This vacuum is not simply nothing. In the quantum world, it is a place full of possibilities where particles can emerge and disappear. The idea of a vibrant and potential-filled vacuum is fundamental to understanding how energy can manifest as matter. With each new particle that arises from these fluctuations, a new component of the fabric of the universe is established. But what about the forces that interact between these particles? Gravity, for example, becomes a key player in the history of the universe. As particles begin to cluster, gravity plays its role in the formation of larger structures, such as galaxies and galaxy clusters. Quantum fluctuations also impact how we understand dark energy and dark matter, two fundamental components that still puzzle us. Dark energy, which seems to be driving the accelerated expansion of the universe, could be related to these fluctuations, suggesting that the vacuum is not something passive, but an active player in the evolution of the cosmos. It's a fascinating cycle. Quantum fluctuations give rise to particles, which in turn create the matter and energy that shape our universe. But what does this mean for us? It means that each of us, at a fundamental level, is part of this cosmic process. We are the result of those quantum bubbles that emerged from nothing and, through an intricate play of forces and energies, shaped the world we live in. Questioning the creation of particles from quantum fluctuations is not just a scientific exploration. It is an invitation to reflect on our place in the universe. Every time we look at the starry sky, let us remember that each star, each planet, even ourselves, are products of a universe that originates from quantum chaos. Deep down, the cosmos is a place full of mysteries, and quantum fluctuations are one of the keys that can help us unravel them. So the next time you think about the vast universe, remember that in its origins, there was a moment when everything was at stake, where small quantum fluctuations took the first step toward the creation of everything we know. Isn't it amazing to think that from nothing, everything can arise? In the vast universe of physics and cosmology, symmetry and its breaking play a fundamental role in how we understand the origin and evolution of the cosmos. But what does symmetry mean in this context? Imagine a perfectly balanced object, like a sphere. In its ideal state, the sphere is perfectly symmetrical, with no side protruding over the other. This symmetry is reflected in many laws of nature, where forces and particles behave uniformly and predictably. But what happens when that symmetry is broken? The breaking of symmetry is a fascinating phenomenon that can give rise to new realities. Let's consider an everyday example. An ice crystal. While in its solid form, it has a symmetrical and ordered structure. However, when heated, the ice melts and loses that symmetry, becoming water, a more disordered state. This change of state helps us understand how, in the universe, the breaking of symmetry can generate completely new and different conditions. In physics, this concept becomes even more intriguing. Symmetry in nature is often associated with the conservation of certain properties, such as energy or electric charge. However, when this symmetry is broken, unexpected phenomena can occur. A classic example is the symmetry breaking that happened in the early universe just after the Big Bang. At that moment, everything seemed to be chaos, but that breaking allowed for the formation of fundamental particles that constitute the matter we know today. The question that arises is, how does this phenomenon contribute to the creation of the universe? As the universe expanded and cooled, conditions changed drastically. The fundamental forces that were once unified began to separate, a process known as symmetry breaking, which allowed particles to acquire mass. This is a crucial step in the formation of matter, as without this breaking, particles would not have the necessary characteristics to form atoms, and thus, matter as we know it would not exist. But what role does quantum mechanics play in all this? At the subatomic level, particles can behave in extraordinary ways. Quantum mechanics tells us that under certain conditions, particles can be in multiple states at once, a phenomenon known as superposition. This principle ties into symmetry breaking, as particles can appear and disappear while interacting in the quantum vacuum, forming a fabric of possible realities that, when symmetry is broken, give rise to tangible matter. Imagine a game of chess where all the pieces are perfectly aligned and do not move. That is a symmetric situation. But when a player makes a move, symmetry is broken and the game transforms, generating new possibilities and strategies. Thus, the breaking of symmetry in the universe acts like a move that allows the creation of new realities, where particles can interact in ways that were not possible before. As we delve deeper into this topic, an intriguing question arises. What if symmetry breaking had happened differently? It could have led to a completely different universe. The diversity of particles and forces we observe today is the result of a delicate balance between symmetry and its breaking. However, it is not just about particles. The very structure of the universe, from galaxies to stars, derives from these interactions. Moreover, symmetry breaking is also related to the unified field theory, which seeks to explain how the different forces of nature are interconnected. This theory suggests that, in its primordial state, all forces were united as one. When symmetry broke, these forces began to take shape, giving rise to gravity, electromagnetism, and nuclear forces. It is a complex process, but essential for understanding how our universe works. Nature offers us countless examples of how symmetry breaking can lead to the unexpected. For instance, in particle physics, phenomena such as the Higgs boson have been observed, which is a fundamental particle that provides mass to other particles. Its existence was confirmed in 2014 and is a clear example of how symmetry breaking can reveal hidden aspects of nature that were previously invisible to our eyes. As we advance in our exploration of cosmology, it is fascinating to think about how symmetry and its breaking not only influence physics, but also have profound philosophical implications. The idea that our universe may have emerged from a state of perfect symmetry, only to break and give rise to the diversity we see today, raises questions about the nature of reality and our own existence. In summary, symmetry breaking is a fundamental concept that helps us understand the complexity of the universe. From the formation of particles to the evolution of fundamental forces, this phenomenon shows us how what appears to be chaos can, in reality, be the precursor to astonishing order. As science progresses, we continue to unravel the mysteries of how symmetry and its breaking shape our cosmos, offering new perspectives on the origin of everything we know. With each discovery, we move one step closer to understanding the majesty of the universe and our place within it. String theory is a fascinating concept that has captured the imagination of many, not only scientists but also those who are curious about the universe. But what exactly is string theory and how does it relate to the multiverse and quantum fluctuations? To understand it, we must first imagine that the fundamental components of nature, those that form the matter and forces we know, are not point-like particles but tiny strings that vibrate. These strings, which are incredibly small, can vibrate in different ways. Each form of vibration corresponds to a different particle. So instead of thinking of electrons and quarks as individual objects, we could imagine them as different musical notes emerging from the same string. Isn't it amazing? This approach not only gives us a new way to look at physics, but also suggests that there could be more dimensions in the universe than we can see. Now, how do quantum fluctuations fit into this puzzle? Quantum fluctuations, those small variations in the quantum vacuum, could be the engine behind the creation of these strings. Imagine the vacuum as a vast sea of possibilities. In this sea, strings can appear and disappear, giving rise to a constantly changing reality. This raises the intriguing idea that the universe could be just one of many realities emerging from these fluctuations. So what about the multiverse? The concept of the multiverse suggests that there are multiple universes, each with its own physical laws and realities. Some of these realities might be similar to ours, while others could be completely different. Can you imagine a universe where gravity is so strong that time stops? Or one where the laws of chemistry are completely different, making it impossible for life as we know it to exist? String theory and the multiverse are not just abstract ideas. They represent serious attempts by scientists to unify physics. String theory seeks to connect quantum mechanics, which describes the world at the subatomic level, with general relativity, which describes gravity and the cosmos on a large scale. In this sense, the multiverse could be a natural consequence of the variations in how these strings vibrate in different universes. Imagine that just as a musician can interpret a song in different ways, strings could give rise to an infinite diversity of universes. Each interpretation would be unique and would, in turn, influence the type of life and matter that could exist. Have you ever wondered if there is a universe where the laws of physics allow for creatures completely different from us? The idea that our universe is just one among many raises profound philosophical questions. If there are an infinite number of universes, what does that mean for our existence? Are we destined to be special in an infinite sea of realities? Or conversely, are we simply a random variation in a vast ocean of possibilities? With each discovery in particle physics and cosmology, scientists find more evidence that could support string theory and the multiverse. Experiments at particle accelerators such as the Large Hadron Collider seek to unravel the mysteries that surround us. Each particle collision could be a window to new dimensions and realities. Meanwhile, string theory has also led to new questions about the nature of time and space. If additional dimensions exist, how does that influence our perception of reality? Could it be possible to travel between universes or even between different dimensions of our own universe? The field of cosmology is constantly evolving. New theories and discoveries emerge almost daily, and each one brings us a little closer to understanding the complexity of the cosmos. String theory and the concept of the multiverse are just a part of this puzzle, but they are crucial for understanding the role that quantum fluctuations play in the creation of our universe. Finally, it is worth reflecting on the impact these ideas have on our understanding of reality. If the universe is the result of vibrations in invisible strings and quantum fluctuations, then our existence, our thoughts and emotions could be the result of a delicate balance in a vast and complex system. These reflections lead us to appreciate even more the wonder of the cosmos and our quest for knowledge. So, when thinking about string theory and the multiverse, let us remember that each discovery is a step closer to the truth. And although there is still much to unravel, every question we ask helps us get a little closer to understanding the mystery of the universe and our place in it. What is that mysterious microwave background radiation that fills the universe, and why is it so crucial for understanding the origin of the cosmos? Let's dive into this fascinating topic. Imagine that the universe is like a large, dark room. Now, if you turn on a very dim light, you'll notice that the light spreads everywhere. That's what microwave background radiation does. It's like the echo of the Big Bang, the first spark that gave rise to everything we know. But how do we know this radiation exists, and what does it tell us about the universe? In 1965, two scientists, Arno Penzias and Robert Wilson, were working on a project and stumbled upon a persistent background noise in their instruments. What they didn't know was that they had discovered something monumental: microwave background radiation. This finding not only earned them the Nobel Prize, but also provided one of the strongest pieces of evidence for the Big Bang theory. But why is this radiation so important? Microwave background radiation is a kind of photograph of the universe when it was very young, just about 300,000 years after the Big Bang. At that time, the universe was an extremely hot and dense place filled with charged particles. As the universe expanded, it cooled, allowing electrons and protons to combine to form atoms. This process, known as recombination, resulted in the creation of photons that now travel through the cosmos, giving us a window into the past. Can you imagine being able to look back in time? That's exactly what the background radiation does. It tells us what the universe was like in its early moments, revealing details about its composition and structure. But what else can we learn from this radiation? Microwave background radiation is incredibly uniform, but it has small variations that are fundamental. These fluctuations tell us how matter was distributed in the early universe. If you think about it, it's like a map that helps us understand how galaxies formed and clustered over time. Without these small imperfections, the universe would be a very different place, perhaps even a place without stars or planets. Now, how does this relate to the quantum fluctuations we mentioned earlier? It's fascinating to think that these small variations in the background radiation may be related to the quantum fluctuations that occurred in the primordial universe. It's as if these fluctuations, which seem so tiny, sowed the seeds of everything we see today. Isn't it amazing to think that there could be such a deep connection between quantum physics and the formation of the universe? Scientists have studied this radiation in great detail, using specialized telescopes that can capture the subtlest differences in the cosmic background. Through these observations, they have been able to map the universe on a scale we never imagined before. This has allowed us to explore fundamental questions: how much of the universe's matter is visible, how much is dark matter, and what about the dark energy that seems to be accelerating the expansion of the universe? Every time we look up at the sky and see the stars, we are witnessing the result of billions of years of cosmic evolution. Microwave background radiation is a reminder that the universe has a rich and complex history. It invites us to reflect on our place in it and how small fluctuations in a primordial moment may have given rise to everything we know today. As scientists continue to investigate this radiation, new questions also arise. Could we someday use this information to unravel the mysteries of the multiverse? What else will the background radiation reveal about the very nature of reality? Microwave background radiation is not just a remnant of the past. It is a powerful tool that helps us understand the present and perhaps even predict the future of the cosmos. It reminds us that the universe is a dynamic and ever-changing place full of surprises and mysteries waiting to be discovered. Thinking about microwave background radiation is thinking about the history of the universe itself, a tale of expansion, transformation, and wonder. So the next time you gaze at the starry night, remember that there is an echo of the Big Bang resonating in the background, a reminder that we are all part of a cosmic story much larger than we can imagine. What really composes our universe? If we look around us, it seems there is more than what we can see. Dark matter and dark energy are two concepts that lead us to question the very essence of what we are and what surrounds us. So, what are these mysterious components of the cosmos? Dark matter is an invisible entity that neither emits nor reflects light, making it practically undetectable through traditional means. But how do we know it's there? Imagine a dance in a dark room. We can hear the music, but we cannot see the dancers. However, by observing how the shadows move and how the light slips between them, we can infer that there are people dancing. Similarly, scientists have observed that galaxies move in a way that cannot be explained solely by visible matter. This suggests that there is something more, which many believe to be dark matter, dark energy. On the other hand, is even more enigmatic. Imagine you are inflating a balloon. As you blow into it, the balloon expands. Now, what if I told you that the universe is in that same process of expansion? In fact, observations show that the universe is not only expanding, but the rate of that expansion is increasing. This is where dark energy comes into play. This mysterious component is responsible for the universe accelerating its expansion. But what if we didn't know it existed? Like an invisible wind pushing the balloon, dark energy is what allows the universe to continue expanding. Now let's think about what this means for our understanding of the cosmos. Visible matter, such as stars and planets, represents only a small fraction of the universe's composition. Dark matter accounts for about 25%, while dark energy makes up around 70%. This challenges our notion of what we consider real. Are we surrounded by things we cannot see or touch? How does this affect our view of the universe? In the context of the formation of the universe, dark matter plays a crucial role. Imagine you are building a house. You need a solid foundation for the structure to stand. Dark matter acts as that foundation, providing the necessary gravity for galaxies and other celestial bodies to group together and form complex structures. Without it, the universe would be a very different place, possibly devoid of the galaxies we know. But how does all this relate to cosmic inflation? The inflation theory suggests that in the early moments after the Big Bang, the universe experienced exponential expansion. During this period, quantum fluctuations may have given rise to dark matter and the structures we observe today. Thus, every galaxy we see, every star that shines in the sky, could have emerged from those tiny fluctuations. While dark matter and dark energy are difficult to study, astronomers have found indirect ways to evidence their existence by observing the light emanating from galaxies and their behavior in groups. They have been able to trace the influence of dark matter on how these galaxies move and cluster. Imagine you are observing a river. Although you cannot see the underground currents, you can infer their existence by how the water flows and behaves on the surface. However, there are many questions that remain unanswered. What exactly is dark matter? Some scientists suggest it could be composed of yet undiscovered particles. Other theories propose that it could be a manifestation of gravity on very large scales. Could there be different types of dark matter? The search for answers continues. Dark energy also raises questions about the nature of the universe. If it is responsible for the acceleration of expansion, does that mean the universe is destined to continue expanding forever? Or will there come a time when the gravity of dark matter prevails and the universe begins to collapse? These are fascinating questions that lead us to reflect on the future of our cosmos. In the philosophical realm, the existence of dark matter and dark energy invites us to question our perception of reality. If much of the universe is invisible and unknown, what does that mean for our quest for knowledge? Are we truly prepared to accept that there is more to the universe than we can perceive? The study of dark matter and dark energy is evolving. New experiments and observations continue to shed light on these cosmic mysteries. As we advance in our understanding, each discovery can change our view of the universe and our place in it. The next time you look at the starry sky, remember that while these bright lights are visible, a large part of the universe remains hidden. Dark matter and dark energy are reminders that the cosmos is a much more complex and fascinating place than we ever imagined. Let us embrace curiosity and continue exploring the mysteries that surround us. For every answer we find only leads us to new questions and a greater understanding of the universe we inhabit. General relativity, one of Albert Einstein's great contributions, revolutionized our understanding of the universe. But what exactly is it, and why is it so crucial for modern cosmology? In this section, we will explore how this theory helps us unravel the mysteries of the cosmos. First, let's think about gravity. We have all experienced its force. When we jump, we fall back to the ground, but in general relativity, gravity is not just a force acting between two objects. It is described as a curvature of space and time caused by the presence of mass. So, when we see a star or a planet, we are observing how the mass of those bodies deforms the fabric of space-time around them. It's like imagining a trampoline. If you place a heavy ball in the center, the surface dips. Now, if you put a marble nearby, it will roll towards the ball due to that curvature. This is how gravity works in the universe. How does this relate to the universe as a whole? When we consider the Big Bang, it is essential to understand that the universe is not only expanding, but this expansion is influenced by the curvature of space-time. General relativity tells us that this expansion is not uniform. It can vary depending on the density of matter in the universe. If there is more mass, the curvature is more pronounced, which can slow down or accelerate the expansion. So, what does this mean for the ultimate fate of the universe? Now, delving into the concept of black holes, we find that general relativity predicts the existence of these mysterious objects. A black hole forms when a massive star collapses under its own gravity, creating a region in space from which nothing can escape, not even light. Its existence is not only fascinating but also raises intriguing questions about the nature of time and space. What happens at the center of a black hole? Some scientists suggest that the laws of physics as we know them cease to apply, opening the door to speculation about what reality truly is. Another fascinating aspect of general relativity is its relationship with time. In this context, time is not a river flowing uniformly. Instead, it dilates or contracts depending on gravity. To illustrate this, imagine two twins. One lives on Earth and the other is near a black hole. The twin who stays on Earth experiences time at a normal rate, while the one approaching the black hole might experience time more slowly. Thus, when they reunite, the twin who was near the black hole may have aged much less. This phenomenon, known as time dilation, makes us rethink our perception of time itself. General relativity has also been tested through astronomical observations. A landmark example is the famous solar eclipse experiment of 1919. where it was demonstrated that the light from stars curves when passing near the sun, just as Einstein predicted. This event not only confirmed the theory, but also catapulted Einstein to worldwide fame. Since then, we have seen how general relativity can predict phenomena such as gravitational waves, which were first detected in 2015. These waves are the result of cataclysmic cosmic events such as the merging of black holes, and provide a new way to observe the universe. However, it is important to note that general relativity is not the only theory that describes gravity. In the quantum realm, gravity behaves differently. Quantum mechanics, which governs the behavior of subatomic particles, does not align with general relativity in certain aspects. This has led scientists to seek a unified theory that combines both large-scale gravity and quantum phenomena. The search for this theory of everything is one of the great goals of contemporary physics. Looking ahead, questions about the workings of the universe become increasingly intriguing. If general relativity describes how space and time behave, what if we discover that there are additional dimensions beyond our perception? String theory, which posits that fundamental particles are actually vibrating strings, suggests that we might have access to a universe much more complex than we imagine. Thus, general relativity not only explains the present but also raises questions about the future of the universe. Will it continue to expand indefinitely? Will it collapse into a big crunch? Or perhaps, as some theories suggest, there could be a multiverse where our reality is just one of many. Human curiosity drives us to seek answers, and general relativity is one of the most powerful tools we have to unravel those mysteries. In summary, general relativity is one of the pillars of our modern understanding of the cosmos. It has given us the tools to understand how gravity and time behave, and has opened the door to questions that still await answers. As we advance in our exploration of the universe, it is essential to continue questioning and seeking, because with every answer we find, new questions arise that invite us to keep exploring. What evidence do we have to support the Big Bang Theory and the existence of quantum fluctuations? This is one of the most fascinating questions in the world of cosmology and may seem overwhelming, but let's break it down to understand it better. First, let's think of the universe as a great book. Every star, every galaxy, and every particle are words in this cosmic story. However, how do we know that this book began with the Big Bang? One of the most surprising pieces of the puzzle is the cosmic microwave background radiation. Imagine that after a great explosion, there remains a faint light that can still be detected. That is precisely what this radiation is, an echo of the moment when the universe was formed. It's as if the universe is whispering its secrets through this light. The cosmic microwave background radiation is like a photograph of the universe in its infancy, at a time when it was an extremely hot and dense place. As the universe expanded, this light stretched and cooled, allowing us to capture it with our scientific instruments. But what significance does this have? It tells us that the universe had a beginning, and that beginning aligns with the Big Bang Theory. Now, what about quantum fluctuations? These small oscillations in the quantum vacuum are essential for understanding how structures in the universe formed. Imagine a calm ocean and suddenly small waves begin to form. These waves are like quantum fluctuations, small disturbances that can give rise to something much greater. In the context of the universe, these fluctuations are the seeds that can grow into galaxies and galaxy clusters. The relationship between the cosmic microwave background radiation and quantum fluctuations is fascinating. Scientists have found that the small variations in the temperature of this radiation correspond to the fluctuations that occurred in the early universe. So, in a way, these small quantum oscillations were responsible for the formation of everything we know today. But how do these observations relate to the theories that attempt to explain the origin of the universe? When we look at the sky and see galaxies, we are not just observing distant lights. Each galaxy is there because there was a process that formed them, and that process is closely tied to the expansion of the universe that began with the Big Bang. Observations of distant galaxies and the way they are distributed in space tell us stories about how the universe has expanded and evolved over time. By examining these galaxies, scientists have been able to confirm that the universe is not only expanding but is doing so at an accelerated rate. This discovery, in turn, raises more questions about the nature of dark matter and dark energy. It is interesting to consider how astronomical observations have evolved. In the past, astronomers could only observe the sky with optical telescopes. Today, we have telescopes that can detect different wavelengths of light, from X-rays to radio waves. This allows us to obtain a much more complete picture of the universe and how it behaves. Experiments like the COBE satellite and the WMAP observatory have been fundamental in mapping the cosmic microwave background radiation. Thanks to these projects, we have been able to gather data that supports not only the Big Bang theory, but also the idea that quantum fluctuations played a critical role in the formation of the cosmos. Each measurement is like a brick in the construction of our understanding of the universe. Some people wonder if there are other explanations for these observations. The Big Bang theory has been tested in multiple ways, but there is always room for skepticism in science. Criticisms of the Big Bang theory often focus on what it cannot explain, such as the nature of dark matter or dark energy. However, each criticism also opens doors to new research and discoveries. The key here is that science is in constant evolution. As we gather more data and improve our technologies, our understanding of the universe continues to change. Each new discovery can offer a new angle from which to analyze the ancient questions about our origin and the nature of reality. In summary, astronomical observations provide us with a map of the universe that supports the Big Bang theory and the existence of quantum fluctuations. Every star, every galaxy, every small fluctuation tells us a story about how we came to be. And as we continue to explore the cosmos, we discover that each answer opens the door to new questions. So, as we keep looking up at the stars, we must never forget that the universe has many more stories to tell. The Big Bang theory has dominated our ideas about the origin of the universe for decades, but what happens when arguments against it are presented? This is a fascinating topic that invites us to question what we think we know. The idea that everything began from a singularity, an extremely dense and hot point, has been widely accepted. However, some argue that this theory is not the only possible explanation for the origin of the cosmos. Firstly, some scientists propose that the Big Bang, far from being a unique event, could be part of an eternal cycle of expansion and contraction. Imagine a balloon that continuously inflates and deflates. In this cyclical model, the universe expands after a Big Bang, then contracts into a big crunch, only to explode again in another Big Bang. Isn't it intriguing to think that we might be living in one of many cycles of the universe? Another criticism of the Big Bang theory focuses on the lack of compelling evidence about what occurred at the initial moment. While the cosmic microwave background radiation is a remnant of the Big Bang, some researchers argue that it could be interpreted in other ways. What if, instead of being a remnant from the beginning of the universe, this radiation were the result of another phenomenon? Science is always evolving, and it is essential to keep an open mind. On the other hand, the standard cosmological model, which includes the expansion of the universe, is based on observations of galaxies moving away from each other. However, could there be other explanations for this phenomenon? Some scientists suggest that gravity might be acting differently than we understand, leading to an alternative interpretation of galactic motion. Imagine looking at a river that seems to flow in one direction, but in reality, its course could be influenced by underground currents that we cannot see. Moreover, the issue of dark matter and dark energy raises more questions for the Big Bang model. These entities are fundamental to explaining the acceleration of the universe's expansion, but what if they did not exist? Instead, we might be observing a phenomenon that does not require these dark concepts. This is fertile ground for speculation and scientific creativity. Often science is based on the search for simplicity, finding the simplest explanation for a phenomenon. However, some argue that the complexity of our current universe cannot be explained solely by an initial event. The idea that everything we see and experience is the result of a single Big Bang may be too reductive. Perhaps the universe is more complicated than we think. Quantum physics also enters the conversation. Could it be that the universe, instead of beginning in an orderly and predictable way, emerged from quantum chaos? This idea suggests that quantum fluctuations, which occur unpredictably, could be the key to understanding the origin of the cosmos. This perspective opens the door to the possibility of multiple universes where each quantum fluctuation generates a new reality. Critiques of the Big Bang Theory are not just an intellectual exercise, they also reflect our need to understand the universe more comprehensively. While the Big Bang has been a cornerstone of modern cosmology, science thrives on questioning and revising ideas. By debating its validity, we are also exploring new frontiers in our understanding of existence. The history of science is filled with theories that, at one time, were considered unquestionable. The geocentric theory, which placed the Earth at the center of the universe, was challenged and replaced by the heliocentric model. Critiques of the Big Bang could be seen as a natural step in our quest for truth. Science often advances through the confrontation of ideas and theories. Ultimately, exploring the critiques of the Big Bang model invites us to reflect on the nature of knowledge. Is it possible that by questioning what we think we know, we are closer to the truth? Every question that arises opens a new path of investigation and discovery. Science is not a destination, but a continuous journey toward understanding. The search for the truth about the origin of the universe is one of humanity's greatest challenges. Alternative theories to the Big Bang are not only a fascinating field of study, but also remind us that curiosity and skepticism are essential in our quest for knowledge. It is this drive to discover the unknown that has led humanity to explore the limits of the cosmos. So, when we face critiques of the Big Bang Theory, we should not see them as an attack, but as an invitation to delve deeper into the mysteries of the universe. Questioning is the first step toward understanding. And on this journey, every answer generates new questions, keeping us always in search of what lies beyond our current understanding. The exploration of the cosmos reflects our own innate curiosity. Alternative theories to the Big Bang offer us a horizon full of possibilities, reminding us that in the vast universe there is always more to discover. What mysteries await revelation in this endless search? The answer, perhaps, is as vast as the universe itself. What if the universe never had a beginning? This idea may sound strange, but it is precisely what the concept of eternal inflation suggests. Imagine a constantly moving sea where each wave represents a bubble of space-time that expands and forms continuously. In this metaphor, each bubble is not only a universe but also the result of an endless process of inflation, a phenomenon that could be happening in a distant corner of reality while we focus on a single universe. Eternal inflation suggests that instead of a single Big Bang that gave rise to our universe, there is a series of Big Bangs, each creating its own universe in a sea of infinite possibilities. What does this mean for us? It means that we could be living in a privileged bubble, while other bubbles or universes could have completely different physical laws. Each bubble could be a universe following its own story, with its own dimensions, forces, and perhaps even forms of life. Why is eternal inflation important? First, it helps explain some of the strange characteristics of our universe. For example, the uniformity of the cosmic microwave background radiation suggests that, on a very large scale, the universe is quite homogeneous. Eternal inflation may be the answer to why regions of the universe that are so far apart from each other seem to be so perfectly aligned. It's as if each bubble has been stretched and smoothed, making them appear more similar than they actually are. However, eternal inflation also raises intriguing questions. If there are infinite universes, where do we fit in? What makes our universe special if there is an infinite possibility of others? One could argue that we are a fortunate coincidence in a vast ocean of possibilities. This idea leads to reflections on the nature of existence itself. If infinite universes exist, is it possible that in some of them there is a version of ourselves living completely different lives? The notion of a multiverse can be disconcerting. How can we prove the existence of other universes if we cannot observe them directly? Science often advances with theories that are difficult to test. Eternal inflation is an example of how ideas can expand so much that they become a challenge to our understanding. However, scientists are seeking ways to detect traces of other universes in the cosmic background or in the correlations of the structures of the universe that we might observe. Imagine you are in a movie theater watching a film that seems to have a clear storyline, but suddenly it is revealed that there are multiple possible endings. Each of those endings represents a bubble in the context of eternal inflation. This is how the idea of the multiverse could be visualized. Each bubble is a different ending. Each universe has its own story. Can you imagine the number of stories that could be unfolding at the same time? This concept also raises fascinating philosophical considerations. If there is an infinite number of universes, does that mean that everything that is possible is also real somewhere, perhaps in some parallel universe? The laws of physics are so different that life develops in ways we cannot even imagine. This type of speculation invites us to think about our own existence, our uniqueness, and the place we occupy in this vast cosmos. As we delve into the mystery of eternal inflation, it is essential to remember that many of these ideas are in the realm of theory. Science is based on observation and evidence, and although eternal inflation is an intriguing concept, more research and evidence are needed to corroborate its validity. Theories must be constantly challenged and questioned, and it is through this process that science advances. So what does all this mean for the future of our understanding of the universe? Research on eternal inflation and the multiverse could open new avenues for understanding not only the origin of the universe, but also the nature of reality itself. As scientists explore beyond the boundaries of our own universe, we may discover surprising connections and revelations that change our perspective on existence. The quest for answers to these questions is not only a scientific journey but also a philosophical one. It leads us to question our own identity, our history, and the future that awaits us. Eternal inflation and the concept of the multiverse are reminders that, although we may feel alone in our bubble, the universe is a vast and often incomprehensible place. In conclusion, eternal inflation offers us a fascinating and complex view of reality. It invites us to dream of the possibility that our universe is just a small part of a much larger whole. And although these ideas may seem distant or abstract, they are a testament to our insatiable curiosity and desire to understand the cosmos that surrounds us. The exploration of these questions is not only a scientific endeavor, but also a journey to the very soul of existence. Quantum fluctuation is a fascinating concept that has captured the imagination of scientists and philosophers alike. But what exactly are these quantum fluctuations? To understand their importance, we must delve into the world of quantum mechanics. In this realm, subatomic particles are not fixed and predictable entities, rather they behave probabilistically. This means that at any given moment a particle can be in multiple places at once and its state is not defined until it is measured. This opens the door to the idea that in the vacuum, where there seems to be nothing, there is actually a constant dance of particles that appear and disappear. Imagine for a moment a calm sea. At first glance, it seems that there is nothing on the surface, but if you look closer, you will see small waves forming and fading away. These waves represent quantum fluctuations, where virtual particles emerge from the vacuum, exist for a brief moment, and then vanish. These small oscillations could be more influential than we think. In fact, they are fundamental to understanding how our universe was formed. What evidence do we have that quantum fluctuations actually occur? A classic experiment that supports this phenomenon is the double-slit experiment. When light is directed through two slits, an interference pattern is observed, as if light is behaving like a wave, but when measured, it behaves like particles. Isn't it amazing to think that the same light can be both a wave and a particle? This behavior suggests that the vacuum is not really empty. It is full of potential, filled with energy that can give rise to the creation of particles. Moreover, there is another fascinating experiment involving the Casimir effect. This effect is observed when two plates are placed very close together in a vacuum. The surprising thing is that these plates experience an attractive force, as if something is pushing them inward. This force is a consequence of quantum fluctuations in the vacuum between the plates. So, in a sense, the vacuum can be a very active place, full of energy that can influence the world we see. But how are these quantum fluctuations connected to the creation of particles in the early universe? Imagine you are in a huge ballroom where suddenly the lights flicker. In that instant, many things can happen. In the early universe, when the Big Bang occurred, quantum fluctuations may have been responsible for causing the first particles to emerge from the vacuum, thus forming the matter that makes up everything we know. The creation of particles is not just an isolated event. Quantum fluctuations can give rise to a variety of processes that influence the evolution of the universe. This includes the formation of atoms, galaxies, and eventually planets. So when you look at the stars in the sky, remember that each one has an origin that can be traced back to those small oscillations in the vacuum. Furthermore, what about dark energy and dark matter? These concepts, which are crucial to our understanding of the universe, may also be related to quantum fluctuations. Dark energy, which seems to be driving the accelerated expansion of the universe, could be the result of these fluctuations in the vacuum. Therefore, by studying quantum fluctuations, we are not only looking at how the universe was formed, but also trying to understand its future. The influence of quantum fluctuations goes beyond cosmology. In particle physics, these oscillations may be responsible for phenomena such as particle decay and the creation of new particles in accelerators. Isn't it incredible to think that what happens in the heart of a particle accelerator may be related to the same principles that gave rise to our universe? As we explore more about quantum fluctuations, we face intriguing questions. What does it really mean that the vacuum is not empty? Could the vacuum be a sea of infinite possibilities that we have yet to fully understand? These questions are not only scientific but also philosophical, inviting us to reflect on the nature of reality itself. Quantum fluctuations, then, are a reminder that the universe is a much more complex and surprising place than we can imagine. Every time we look at the night sky, we are looking at a reflection of a past filled with chaos and creation, all thanks to the small and ephemeral fluctuations that shape our reality. Ultimately, these oscillations teach us that the origin of the universe is not just a story of great explosions, but also of small fluctuations that, in their apparent insignificance, have given rise to everything we know. So, the next time you think about the universe, remember that even the vacuum has its own story to tell. The idea that the universe could have emerged from a simple quantum fluctuation is undoubtedly a fascinating concept. But what does this really mean? What implications does it have for our understanding of reality and our existence? Let's explore these questions and reflect on the profound philosophical implications that arise from this idea. First, let's think of the universe as a vast ocean. This ocean is filled with small waves that constantly appear and disappear, even in the calmest parts. In this case, the waves are the quantum fluctuations, small variations in the vacuum that can, in theory, give rise to the creation of particles and eventually to everything we know. If the universe began this way, isn't it astonishing to think that everything we see, from stars to planets, could have arisen from something so ephemeral and small? In philosophy, the notion that something can arise from nothing raises deep questions about the nature of existence. What does nothing really mean? If the quantum vacuum, which seems to be the most basic state of reality, can give rise to things, what implications does this have for our beliefs about creation and existence? The idea that the universe may have emerged from a quantum fluctuation challenges many of our traditional notions about origin. Let's consider the possibility that if the universe began this way, we might be living in a cosmos where creation is an intrinsic property of reality itself. This leads us to wonder, is the universe a place where life and matter can naturally arise like a river flowing effortlessly? If so, our lives could be the result of a larger cosmic process where each of us is a wave in that vast ocean. The concept of quantum fluctuations also leads us to question our perception of time. If time is an illusion, as some interpretations of quantum mechanics suggest, what does this mean for our daily experience? In this sense, reality could be much more malleable and dynamic than we believe. Instead of a clock moving linearly, we might be in a space where time and space are intertwined in ways we do not yet fully understand. The idea that the universe could exist in a state of constant creation also invites us to reflect on our connection to the cosmos. If we are the result of a quantum fluctuation, does this mean that we are all interconnected in some way? That our lives, thoughts, and actions are part of a larger cosmic fabric? This interconnectedness could be a source of wonder and humility, reminding us that we are part of something much greater than ourselves. In Eastern philosophy, there is talk of the idea of the oneness of all. This notion resonates with the idea that the universe could have emerged from a quantum fluctuation. If everything is interdependent, then every action we take could have an impact on the cosmos. How would this change the way we live and treat others? The understanding that we are part of a whole could inspire us to be more compassionate and mindful of our actions. On the other hand, the notion that the universe can arise from nothing also raises questions about the concept of causality. If quantum fluctuations can create particles and energy from nothing, does this mean that causality, as we understand it, could be more complex than we think? Perhaps there are aspects of reality that elude our understanding and challenge the laws we believe govern the universe. As we reflect on these ideas, it is also important to consider the impact they have on our understanding of life after death. If the universe is in a constant state of fluctuation and creation, could it be that our consciousnesses are also part of this process? Could it be that life and death are simply two sides of the same coin, a continuous cycle of transformation in a constantly changing universe? We must not forget, moreover, the sense of awe and wonder that these ideas can inspire. Imagining that the universe, with all its complexity and beauty, may have arisen from a simple quantum fluctuation is a reminder that there is much more to reality than we can see. It invites us to be curious, to explore, and to question. Every discovery in science not only brings us closer to the truth, but also opens the door to new questions. Finally, the notion that the universe could have emerged from a quantum fluctuation leads us to a place of humility. It reminds us that despite our achievements and advancements, there are still mysteries in existence that we do not fully understand. This space of uncertainty can be uncomfortable, but it is also a fertile ground for exploration and discovery. So, as we contemplate these philosophical implications, let us remember that every question we pose and every answer we find is part of our endless quest to understand our place in the cosmos. The idea that the universe could have emerged from a simple quantum fluctuation is just the beginning of an amazing journey, filled with intriguing questions and infinite wonders. Theories about the origin of the universe are like ancient maps. Each offers a different perspective, but all attempt to guide us toward the same destination. One of the most intriguing theories is the cyclic model, which proposes a vision of the cosmos in constant rebirth. How does this idea compare with the Big Bang theory and the quantum fluctuations we have explored? To understand it, it is essential to unravel the essence of the cyclic model. In this model, the universe has no defined beginning or end. Instead, it is imagined as an endless cycle of expansion and contraction. Picture a huge balloon that inflates and deflates, expanding to unimaginable limits and then eventually collapsing back to a point. This collapse could give rise to a new Big Bang, generating a new universe with new laws and possibilities. But what implications does this vision have for our understanding of the cosmos? One fundamental question that arises is, what triggers these cycles? Some scientists suggest that gravity plays a crucial role in this process. As the universe expands, galaxies move apart. However, over time, gravitational attraction could be strong enough to halt that expansion and cause a collapse. This life cycle of the universe is fascinating, but it also raises doubts. Could there be evidence to support this idea? On the other hand, the cyclic model faces a significant challenge: entropy. The second law of thermodynamics tells us that entropy, or disorder, in a closed system never decreases. This means that with each cycle, the universe could become more chaotic. If the universe restarts after each collapse, how is the coherence of physical laws maintained? Some theories suggest that despite entropy, the universe could find ways to balance itself before each new cycle. But is this enough to maintain the continuity of the cosmos? Another theory that has captured the attention of many is the creation from nothing. This idea, often associated with quantum fluctuations, holds that the universe can spontaneously arise from a quantum vacuum. Could it be that, at some point, the cyclic universe and the universe of quantum fluctuations are two sides of the same coin? Perhaps these approaches are not as different as they seem, and maybe both attempt to explain the same reality from different angles. Delving into the realm of philosophy, the notion of a cyclic universe raises intriguing questions about time and existence. If the universe has infinite cycles, what does that mean for our understanding of time? Is time a linear river flowing forward, or is it more like an ocean of cycles in which everything that has existed can come back to exist? This perspective could offer comfort to those seeking answers about life and death, suggesting that the end of one existence is merely the beginning of another. However, the cyclic model is not the only contender in the ring of theories about the origin of the universe. String theory, for example, introduces the idea of a multiverse, where multiple universes coexist, each with its own physical laws. How does this relate to the notion of cycles, perhaps in a cyclic multiverse? Each universe could have its own cycle of expansion and contraction, creating a vast tapestry of interconnected realities. In this context, the idea that each universe in the multiverse may be influenced by quantum fluctuations becomes even more fascinating. If each of these universes can arise from a quantum vacuum, then the creation of universes could be a common process, a phenomenon that repeats in a vast space of possibilities. This raises a new question. How many universes can exist before chaos takes over creation? Another theory that has been discussed is loop quantum cosmology, which suggests that space and time are discrete rather than continuous. This could provide an explanation for the stability of cycles in the cyclic universe. Is it possible that by dividing time and space into smaller units, a balance is achieved that allows cycles to repeat without falling into chaos? This idea remains a subject of debate but opens new avenues for exploration. Comparisons between these theories not only enrich our understanding of the cosmos but also reveal humanity's innate curiosity to discover its place in the universe. Each theory, each unanswered question drives us to continue investigating and exploring. What other secrets does the universe hold in its vastness? Perhaps we will never know all the answers, but it is in the journey of discovery where true wonder resides. Finally, it cannot be overlooked that each of these theories provides a unique perspective on the origin and nature of the universe. Science, like a great puzzle, offers us pieces that, although sometimes seem to not fit together, invite us to keep searching for the complete picture. As research advances, new theories and discoveries are likely to emerge that challenge our current understanding. Thus, the mystery of the universe remains alive. And with each question we answer, even more questions arise. What will be the next discovery that makes us reconsider everything we think we know about our cosmic home? The search continues, and with it, the essence of what it means to be human. Future research in cosmology is not only a journey into the unknown, but also awakens an insatiable curiosity about how our universe was formed. What mysteries remain to be unveiled in this vast ocean of stars and galaxies? Each new answer brings more questions, like a puzzle that never stops growing. Modern cosmology is constantly evolving, and every technological advance opens new doors to the exploration of the cosmos. One of the most promising fields focuses on the exploration of dark energy. What is this force that seems to be accelerating the expansion of the universe? Dark energy represents an enigma that intrigues scientists. Like an invisible wind pushing a boat through water, this energy seems to act in the background of cosmic expansion. As telescopes and satellites improve, researchers hope to gather more data that will help understand the nature of this mysterious energy. Dark matter also remains a hot topic of research. Why can't we see it, yet we know it's there? It's like a ghost that influences the structure of the universe. Scientists are developing more sophisticated experiments to detect dark matter particles. Each new discovery could be a clue that brings us closer to understanding how this invisible matter has shaped the galaxies and other celestial bodies we see today. The search for gravitational waves is another field that promises to revolutionize our understanding of the cosmos. These waves are like ripples in a pond caused by massive cosmic events, such as the merging of black holes. Detecting these waves not only confirms existing theories, but also opens a new channel of communication with the universe. What secrets could they reveal to us? Each time they are detected, we get a little closer to understanding the processes that shaped our universe. Moreover, the exploration of planets outside our solar system, known as exoplanets, is intensifying. Are there other worlds that harbor life? With each new finding, the possibility of civilizations existing in other corners of the cosmos becomes more real. Space missions are designed to study the atmospheres of these planets and search for signs of biological activity. This search is not only scientific, but also deeply philosophical. What does it mean to be human in a universe full of potentialities? artificial intelligence is beginning to play a crucial role in cosmology. How can machines help us unravel the mysteries of the cosmos? With their ability to analyze large volumes of data, artificial intelligence can identify patterns that the human eye might overlook. This could lead to astonishing discoveries, helping scientists formulate new theories about the evolution of the universe. We cannot forget the role of simulation in cosmological research. Scientists are creating computer models of the universe to test theories and understand complex phenomena. To what extent can a simulation reflect reality? As these simulations become more detailed, we can begin to see how quantum fluctuations and other phenomena influence the structure of the universe. International collaboration is also taking a leading role. How far can we go if we join forces? Projects like the James Webb Space Telescope, which brings together scientists from around the world, promise to provide a clearer view of the early universe. Global cooperation not only accelerates progress, but also fosters a sense of community in the quest for knowledge. Next-generation telescopes are on the way and promise to revolutionize our view of the cosmos. What discoveries await us on the horizon? Equipped with advanced technology, these telescopes will allow us to observe more distant and ancient objects than ever before. Each new piece of data could be a key to unlocking the mysteries of the universe's origin. In this exciting journey of discovery, cosmology confronts us with fundamental questions. What is our place in the vast universe? The study of the cosmos is not just a scientific quest, it is also an exploration of our own existence. Each answer leads us to new questions, creating an endless cycle of curiosity. The intersection between science and philosophy is more present than ever. What does the idea that the universe could have emerged from a quantum fluctuation imply? This is not just a scientific question, but also a question of meaning. Cosmology invites us to reflect on our own nature and the role we play in this vast web of energy and matter. As we move toward the future, the frontiers of knowledge are expanding. How will technology change our understanding of the cosmos? Advances in observational technology and data analysis promise to take us to a new level of understanding. What we consider science fiction today could be a reality tomorrow. Each discovery reminds us that there is still much to learn. Human curiosity is a powerful engine, and cosmology is a field that not only informs us but also inspires us. How far will this quest for knowledge take us? The answer is in our hands, and the universe patiently awaits our exploration. Finally, the future of cosmology is filled with exciting possibilities and unknown threats. What surprises does the cosmos hold for us? The quest to understand our origins and the workings of the universe continues, and each step we take in this direction brings us a little closer to unveiling the great mystery that surrounds us. The adventure is just beginning, and each of us is part of this cosmic story. As we delve into the fascinating world of quantum fluctuations and their role in the creation of the universe, it is essential to reflect on what we have learned. What does it really mean that the universe emerged from a simple fluctuation? The answer could change our perspective on existence itself. Let's consider how science and philosophy intertwine in this vast universe we inhabit. The idea that everything we know could have started from a tiny point in the void is undoubtedly intriguing. How is it possible that from nothing, or from a quantum vacuum, all the matter and energy we see today arise? This leads us to question the very nature of reality. Is the vacuum truly empty, or is it filled with potentialities waiting to materialize? Exploring the Big Bang Theory and cosmic inflation, we encounter an epic tale about the origin of the cosmos. Just like a grand explosion of fireworks lighting up the sky, the Big Bang marks the beginning of our universe. However, it becomes even more captivating when considering that this initial explosion may have been fueled by quantum fluctuations, giving rise to the creation of particles and eventually the stars and planets we know. Quantum mechanics offers us a window into the strange and wonderful behavior of subatomic particles. Scientists have discovered that this behavior may seem chaotic, but there is an underlying order that piques our curiosity. What other secrets does this tiny world hold, so far removed from our everyday experience? The connection between the quantum and the cosmic is fundamental to understanding how the universe formed and, in turn, how it influences our daily lives. The idea of a multiverse emerges as a fascinating possibility. What if our universe is just one among many? This concept, although difficult to digest, opens the door to a variety of realities. Imagining alternative universes where the laws of physics are different may seem straight out of a science fiction novel, but science is beginning to explore these ideas. What implications would this have for our understanding of life and the universe? The quantum vacuum itself raises profound questions. The notion that the vacuum, something we consider as the absence of matter, can be a hotbed of quantum activity is astonishing. This leads us to consider the nature of existence. Is matter the rule or the exception? This questioning is essential to our quest for knowledge. Quantum fluctuations are not just a phenomenon in the lab. Their impact extends to the formation of structures in the universe. Small variations in the density of the early universe led to the creation of galaxies and galaxy clusters. What other mysteries about the cosmos could be revealed if we continue exploring these phenomena? Moreover, string theory and symmetry breaking show us an even more complex landscape. Symmetry is a fundamental characteristic of nature, but its breaking can give rise to new realities. Could it be that the creation of the universe is intrinsically linked to the loss of symmetry? Reflecting on this invites us to rethink our beliefs about order and chaos in the cosmos. The cosmic microwave background radiation, that echo of the Big Bang, becomes a valuable clue. By studying this radiation, scientists can glimpse the conditions of the universe in its early stages. What other traces of the past remain hidden, waiting to be discovered? The quest for these answers is one of the greatest adventures in modern physics. As we delve into dark matter and dark energy, we realize that the universe is a mysterious and enigmatic place. These invisible forces seem to dominate cosmic structure, challenging our understanding of gravity and matter. What other surprises await us on this journey of discovery? The journey through general relativity reminds us that time and space are intrinsically connected. This theory revolutionized our understanding of the universe and has been confirmed through countless experiments. How do these concepts relate to the creation and expansion of the universe? The challenge of understanding the Big Bang has led to critiques and alternatives. Science is in constant evolution, and each new theory adds another layer of complexity to our understanding. Are we close to unraveling the mystery of the universe's origin, or is there more to discover? Eternal inflation, with its promise of an expanding multiverse, leads us to consider that the universe is not static, but dynamic and ever-changing. This idea raises questions about our place in the cosmos. Are we alone in this vastness, or are we part of a much larger tapestry? Finally, looking to the future, cosmology remains a vibrant and growing field. New technologies and approaches promise to shed light on the mysteries that still elude us. What revolutionary discoveries are just around the corner? Every question we answer seems to open the door to many more. In conclusion, the exploration of the origin of the universe and quantum fluctuations not only offers us a deeper understanding of our surroundings, but also invites us to reflect on our existence. Science and philosophy intertwine in this quest, reminding us that while the universe may have begun in an extraordinary way, our curiosity and desire to understand it are equally astounding. So let us continue exploring, questioning, and discovering, for the universe has many more stories to tell us.